Yeah, just like The Office. Hello, virtual students. Welcome to the 4.5 to 4.6 matchup. We are so happy you are here. Thank you for watching.
Yeah, that's how it's gonna go. Pretty sure that's the same.
I'm 1000% sure they.
That means I need to stay up here too, otherwise they won't be able to hear me. So I need to be stuck up here. Don't let me walk around.
Don't walk around.
Sit down in your fancy chair on your stove.
Which one?
We got half
No, that's mine. Sorry, Amazon.
Yeah, so you decreasing.
Hey, you stole it from Amazon?
Yes.
How dare you?
Did you steal it?
Wow.
All right, here we go. Let's take a look here. Now we are increasing and decreasing. We are going from left to right, and we are thinking about what is happening to our y values as we get close to this minimum right here. Now, our y values continue to decrease as we come closer to that minimum. So we would say that our function is decreasing when x is less than 1. And then after we hit this minimum, we start to increase for a little while. So we're increasing from 1 to 3. And then after we hit this maximum, we are decreasing again. So when x is greater than 3, we begin to decrease again.
That's good.
That's good?
Yeah.
Oh, good. Now, one thing to point out, and this is vocabulary that comes up in, I think, 4.7, but we'll talk about it now since it's a mashup. Maybe it's 4.6. We would call this point right here. It's not the minimum, and you might want to label this on your sheet as well. We wouldn't call it the minimum. It is called a local minimum, because this keeps going down and down and down forever and ever and ever. So the actual minimum would be negative infinity, but still this is a minimum point, so it's called a local min. If that's a local min, what do you think this is?
Local max.
Good guess, actually, but it's a local max. So we would just call that our local minimum and local maximum, kind of as a side note, but that's good vocabulary to know. Now, as we look at when f of x is greater than 0 or less than 0, that's just talking about when we're above or below the axis. So we are above the axis when x is less than negative 2. Also, we are above the axis between 2 and 4. Right, just above or below. Now we are below the axis from negative 2 until 2. And then we are also below the axis when x is greater than 4. Is any of this ringing a bell so far?
Yes.
Absolutely? Not. Okay.
Well, kind of.
What? We do. Yep.
I mean, like, I remember, like, the increasing and decreasing.
Okay, good. The above and below the axis you might not remember, but I don't think, I could be wrong, but I don't think that that's an overly difficult concept. Just when our line is above the axis, just when it's below. Maybe the most difficult part is using this notation to write it, but I think you can all recognize when the line is either above or below the axis. Now, how do we figure out if this is an odd or even, if we're going over here, if this is an odd or even degree, or what the leading coefficient might be? How do we even begin to try to think about that or figure that out? Yeah, Braden?
Look at your note sheet.
Yeah, we can look at that note. You could almost call it a note packet from the very first lesson from 4.1. There was that chart at the very end of it that showed the n behaviors.
And it shows what they look like.
Yep, and we can look at that chart and look at those graphs and see which one of the graphs had it so that as, well, maybe we should go over here first. As x approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches positive infinity. So we would want to see which graph matches this end behavior here. So would that be a graph that has an odd or an even degree? An odd degree and a positive or negative coefficient.
Hey, I guessed on that.
Good job.
Good job. Now, one thing to think about, like big picture with all this kind of stuff, with this odd or even degree or leading coefficient, if we spent a lot of time looking at parabolas, and this parabola that I drew on, first, do parabolas have an odd or an even degree? Even. Parabolas are squared. Now, in this case, with the one that I drew, would the coefficient be positive or negative? So if we can, even though, like this would be, x squared. If we had something that was like x to the fourth, it would have more humps in the middle, but the end behavior would still be the same as our parabola, as long as it was an even and a positive leading coefficient. So even though things might look a little bit different if it's 2 to the 4th or 2 to the 6th or 2 to the 8th or whatever, we still know that that end behavior will act the same as a parabola with a positive coefficient or a parabola with a negative coefficient. So that's pretty sweet.
So that's pretty cool.
All right, what do we still have left? Oh, some factoring.
Ew.
Let's see.
That's gross.
That is good.
What is the greatest common factor of these three numbers? 3x. So then we write the leftovers. We would have x squared minus 4x minus 12.
Yes.
And then we can continue to factor here. 3x, x. Can you guys see that kind of? Yeah. X and x. Then we have to multiply to get negative 12, so that means a plus and a minus. And then we have to add to get negative 4, so that would be 2 and 6. Now we factor all the way out. What strategy do we need to use for the next one? Yeah? What do we need to do, though?
We need to split them up into.
We need to chunk it up.
Please don't ever say that again.
Chunk it up.
Stop! That ain't
Hey,
it.
Kylie, take it
That's
easy.
worse than the dang One Direction song.
No, it's not. It is not.
Quadratic formula song, bro.
We could listen to that.
That was a certified good class.
Now that we chunked it up and factored out what we could, now what do we do? What can we factor out of this big term and this big term? What do they have in common?
The little parentheses.
Yeah, the x plus 3.
That's it. Wow. I did not listen when you teach this.
Evan.
Good.
Good.
Because
It's just the two
after-
things outside the parentheses.
Yep, so we take this and factor it out, then the leftovers are x squared and 4. So we can write those inside of parentheses together. Plus 3 squared.
It can be
So we
x
took-
squared plus 2
I see where you're coming from,
What
Jack.
happened to the other?
We looked at this big term and this big term, and we factored out both of them, an x plus 3. And then we just can write the leftovers, the x squared and 4, inside our parentheses. Kind of a weird rule that doesn't quite
Makes
look right,
sense.
but if we were to factor it back out, we would get
That's silly.
that back.
Did we chunk it up?
We did chunk it up, or factor by grouping. So that was a good review of what we did 2 weeks ago.
Yeah.
Now, we are going to, like I said, move forward and hit the highlights of 4.5 and 4.6. Yes. What you're going to see is, like it says on the next slide, I'm going to do some of your homework for you, and then you are going to go ahead and do some of your homework on your own. On which one? Which part of it? Right here? After we factor the x plus 3 out, then we can just write the leftovers in parentheses. So our leftovers were x squared plus 4 in this case. Good? Okay. All right, so let's look at your piece of paper, and let's look at 4.5, number uno. The paper copy. Yep, 4.5. Numero uno. Yep. Yep. Now it says in exercise 1 through 6, solve the equation. So if you looked at, let's ignore the equals sign for a second. If you look at q cubed minus q squared minus 30q, well, I should probably write down the problem on here. Q cubed minus q squared minus 30q equals 0. If we ignore that equal sign for a minute and we just looked at the left-hand side and I asked you to factor that out, you would look at each of these terms and say, hey, they each have a q. And then what would you do with those parentheses? Or what would you do with what's left inside the parentheses? Yeah, we'd factor it. We'd set up our two sets of parentheses, and we'd say, what can we multiply together to get negative 30? Well, that means we're going to have a plus and a minus. And then add together to get negative 1. Well, if we start thinking about factors of 30, we have 1 and 30, 2 and 15. Come on, I was going to get there. Build up the excitement. 3 and 10, 4 doesn't work, 5 and 6. Oh, winner, winner, winner. Times 5, or 5 times negative 6 would give me negative 30. 5 minus 6 would give me negative 1. Now, if we were factoring it and there wasn't an equal sign equal to 0, anything like that, we'd be all set. We'd be good to go. But since it says to solve, after we... Yeah, there's just one more little step. After we factor it, we have to look at each of our terms here, and we need to see what would make each one equal to 0, because these are being multiplied, right? So if any of our terms become 0, then the whole thing zeroes out. So if we look at this first q, what would make this first q equal to 0?
Put it 0.
0. So if we plug 0 in, then this whole thing will zero out. What about our second term? What would make this second term equal to 0? Negative 5. And what about the third? 6. So when it says solve the equation, our three solutions would be 0, negative 5, and 6. Yep.
Wow, that's crazy.
That makes sense?
Yeah.
Good. Now you can go ahead and do, where'd it go? You can begin working on number 4, 2, 4, and 6. You can cross out number 3 and number 5. You do not need to do number 3 and number 5.
Bro, I was gonna do 5.
So, no, cross out. I thought you'd be locking in when I say cross out right away, Alton. I thought that would be... Oh, okay, gotcha. Cross out number 3 and number 5. Yep. So, well, on this page, yeah. You have until big hand on the 7 to work on those on your own. I want you to try number 6, but there's a little trick involved with number 6. Yep. So we might need to work on that together, but I want you to give it a try. Yeah, you get to chunk it up. Number 4.
No, stop.
So number 2 and number 4, well, and in number 6, you'll look at the problems, you'll factor them just like we've been working on or like we worked on last week, 2 weeks ago. And then the only stuff that we'll be adding is we need to write those solutions. Yeah, so you gotta, yep, you gotta chunk it. Chunk the first 2, chunk the second 2. If you need a little guidance on chunking, you can look at that first piece of paper I gave you that was handwritten. The very last problem on there is one that I chunked.
So when we like switch it to a, switch it to like plus sign, you can't subtract.
If you, I think it's easier, yes. If you make it a negative 9n, yeah, and put plus in the middle. And then you would factor out a negative 3 out of the 9n and negative 18, or negative 9n, negative 18.
Why not 9?
Oh, sorry, yes, factor out 9. Yes, that's what I did.
Yeah, that seems way easier.
It is, good call.
Gotta be.
It won't actually work if you don't factor out a negative 9.
Wait, so you would make the negative 9n just 3n?
So,
No, you make it. And there's a trick on number 6. No, any of us.
or is it 2n squared? So we have this, right? Is that big enough, or do I need to write a little bigger? Okay. Then when we chunk it, I would chunk it like this with the negative sign here, and put a plus sign in the middle. So then you have n cubed minus 2n squared plus a negative 9n minus 18. I think that's a little easier to think about.
When you factor out the 9, would it be negative 1n plus 2?
So then, yeah, when you factor, I think this one you guys get, no big deal. But then here, when you factor, I would factor out a negative 9 out of both.
So you just make it n plus.
Wait, how is your?
Plus 2?
Oh, did I switch a sign somewhere? Is this a plus?
Yeah, that's a positive.
Okay, that makes sense. So I would factor a negative 9 out of here. So then you have negative 9 n plus 2.
Wait,
No, it's 9 plus negative. Because that negative 8
Yes.
is plus 8.
So then we're here.
No, that 18 is positive.
no, it isn't.
No, it's not.
I get to switch it.
Once we factor a negative 9 out, then it turns. That's what turns it positive.
Well, doesn't it switch positive when you turn into like addition to
Here?
Yeah.
No, because you just, I mean, this was negative. You just rewrote this as plus a negative 9n.
Yeah, you're right.
You know what I mean? It's already a negative 9n. We didn't like multiply this whole thing by negative 1. We just rewrote it.
And then would that just be the final answer then?
Well, now we need to look at what does this, what do these two have in common? What can we factor out of these two both? Well, big term, n plus 2. Oh, that's weird.
There is no thing. Still able to do that.
What?
You ate off the paper?
Something like that.
See, told you. How do we do number 8?
All right, let's look at, oh, big hands past the 7. Let's look at, we got to keep moving today. Let's look at number 6. So first we need to get this set equal to 0. Perfect. Now what can we factor out of both terms? We good so far? Now, when we start to look to solve, or start to look to see what would make these two terms equal to 0, what would we need to plug in for u with this first, with this 8u to the fourth? What would we need to plug in for u to make it equal 0? 0. Now, here with u squared minus 2, it's a little bit more difficult to see. But we are allowed to just write a little equation to see what would make this equal to 0. Because like earlier here, really, I mean, we did 6 minus, or q minus 6 equals 0 to figure it out. But we could see that a lot easier. But now that it's u squared minus 2, it's kind of difficult to think, okay, what could we put in for u to make it equal to 0? And then what would we need to do to solve? Yeah. Plus and minus the square root of 2.
I just wrote them as two separate terms.
Yep, that works too. Yep, if you want to write one positive and one negative. But that's the little trick there in number 6. The factoring part of it and all that is no big deal. But seeing what would make this term equal to 0 can be a little bit tricky. Yeah. How about for which one? Well, number 4 is a little bit different because in number 4, what would make this first term, n plus 2, what would make this first term equal to 0? Yeah, negative 2. Now, what could we put in for n to make this
Or negative.
3 and negative 3? Yep. I mean, you could, this is a little easier to see because 9 is a perfect square, but you could write an equation, kind of. Well, not kind of, write an equation.
Definitely an equation, actually.
And you could solve. But like, if this is a perfect square, if this is 9, 16, 25, anything like that, it is a little bit easier to see what that would need to be.
There's not a lot of those, though.
A lot of perfect squares or a lot of questions like that.
Perfect.
Yeah. Okay, let's keep moving.
7.
Now, as we look at the backside, we are going to be solving, and then they're going to have us be graphing. Now, here's a general rule that might be helpful to write down if you're taking separate notes. If we have, I mean, first they use this language x minus k. X minus k is just something like this, where we have our parentheses, x or n or whatever the variable is. Minus is the default, but then a number. So when we set up our two sets of parentheses, those are both in the form x minus k. But when x minus k is raised to an odd power, like this is raised to 1, the graph goes across the x-axis, right? We know that this is one of our intercepts. If x minus k is raised to an even power, like it says in this other side, then the graph just touches the x-axis at that point. Is 0 an even power? No, 0 is just 0. Nothing's raised to 0 because that would just be 1. So you'll see how this rule comes into play in just a second. Well, right now. So let's look, it's over there. Let's look at the backside. I'm going to do number 7 for you. We have, with number 7, f of x equals x to the 4th plus x squared cubed? Cubed. See? This is
7.
the back number 7. Now, the directions say find the zeros of the function, so that means we need to have this equal to 0 and solve to find the zeros, and then we need to sketch a graph. So first, let's find the zeros. Factor out an x squared. Plus 4 minus 3. Whoops. So first we factored. Now, based on what we talked about on the last page, what would we do to find the zeros? What are our zeros? What makes this 0? What makes this 0? And what makes this 0? So, good. If we look at our graph now, and you need to sketch a graph, the rule we just looked at said that if our term was raised to an even exponent, then that means that it touches the x-axis at that point but doesn't cross. If it's raised to an odd exponent, then it crosses. So we know our key points are going to be -4, +3. So at -4, 0, and +3, something is going to be happening. Now, as we start to sketch our graph, we need to figure out, does our graph come in from this way and then loop-de-loop through here? Does it come in through here? Which way is our graph coming from? Which way is it starting out from? And we can figure that out by looking at the end behavior of our graph. If you remember back to our review, if we look at this leading term, we have a degree that is even and a leading coefficient that is positive. So when we have a degree that is even and leading coefficient that is positive, we know that our end behavior will look something like this. That as x approaches infinity, y will be approaching positive infinity. As x goes to negative infinity, y will be approaching positive infinity. So we need to keep in mind our end behavior as we are graphing these. Now, like our rule said, if we have something that is raised to an odd exponent, like x plus 4 is, then that means we go through it. So we go through -4. Now when we start to come over to 0, x is raised to an even exponent. So what does that mean our graph does? Does it go through it? No, it just touches and then keeps going. So it touches here, and we keep going. Now we come back to -3, which is raised, +3, which is raised to an odd exponent, means that we cross it. So our graph, and it doesn't have to look exactly like this, but our graph would look something similar to this. It is possible that our graph maybe goes further down and then comes up and goes further down, but I would be expecting to see something close to what I have here. Do you see how we're bringing together like 3 different concepts that we've talked about? Okay. Why don't you go ahead and work on numbers. Why don't you do number 9 and number 10? You can cross off number 8. Don't put a big X through it. We may come back to it tomorrow for like a warm-up or something like that. But for right now, did you already put a big X? Well, you're writing on your iPad. You can easily erase that. Or no, this is the paper one, isn't it? That's okay. If you put a big X through it, we'll figure it out. But be working on number 9 and number 10. Sorry, not yet.
I didn't get any sleep.
I mean, like, you can go home. I can't stop you, but...
I was up too late playing my part garage.
We'll go to a big hand on the 10 on those. Your first step is to solve for the zeros, just like we did on the front page. Your next step is to look at the degree and the leading coefficient so you can figure out what that end behavior might look like, and then you'll be able to sketch a graph.
Like that?
About 2 more minutes to work on those bottom 2 questions.
I may have done that.
Yeah.
No, I
Oh my god.
understood.
Supposed to be
Here is the general shape of what, I mean, you need a factor, you need to do all that stuff, but that's about what number 9 and number 10 should look like on your graph. So you can at least see if you're tracking. In both problems, you have everything raised to an odd power. You don't have anything that is a touch and go because all of them are raised to an odd power. About one more, well, not even a minute, about 30 seconds to finish those up. If you don't get every single one done right now, that's okay. What? Need more time? Well, we still need to break into 4.6 a little bit here.
Start by doing
Kind of. Well, we just used that review that was on that worksheet. All right, about 10 more seconds. Get to a good stopping point with the one you're on. Number 9? Yeah, number 9 is odd and positive. Oh, number 10 is odd and negative. All right, so now we're going to move to 4.6. And you don't need to write this whole thing down, but I'm just making you aware of this theorem. You don't need to write the whole thing down. We will use the corollary a lot. pretty much, here, back with me. You don't have to have this theorem memorized or even really remember the name of it too much, but you do need to know what the rule says. And what this rule says in general is said in the corollary. If f of x is a polynomial of degree n, so if we have some function that's raised to, or that has degree 4, then the equation has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, each solution repeated 3 times is counted as 3 solutions, and so on. So what that means, and we had a good example of it earlier, here, is if we have some function like this, f of x equals 3, or q cubed, and we look at the degree of this function, it has a degree of 3. That means that this function has 3 solutions that we can find. If we have a function like this that's raised to degree 6, that means, or that has a degree of 6, that means that this function has 6 solutions. Now, like it says, that is granted, or that is saying that since it's u to the 4th, that means that we would count 0 4 times. So that's how this rule applies. So we'd have 4 zeros and then a positive root 2, negative root 2 to get up to 6. Here, this has a degree of 4. So that would mean that we have 4 solutions. Again, 0 is counted twice because it's squared. You could put 0 in for x, right? Squared just means there's 2 x's. So you could put 0 in for x, 0 in for x, negative 4, and 3 to get us up to a degree of 4 with 4 solutions. Now, what comes into play, well, we'll get to that in a second. Let's look at now 4.6 and look at the first, it's labeled number 9 and number 10, but look at the first 2 questions. Oops, sorry. One more thing I need to cover first. If we have a graph what if we have a graph that's like this? X squared plus 6. 1, 2, 3, 4, 5, 6. That's right here and like this. According to that rule we just talked about, how many solutions does it have? It has 2 solutions. Now, what is the problem with saying that right now? What kind of solutions will they be? If we were to solve this for our solutions, what kind of solutions would these be? Imaginary. Now, one rule that's extremely important to keep in mind is when we are counting solutions, anytime we have imaginary solutions, they always come in pairs. So on this next worksheet, it's going to be asking how many positive, how many negative, and how many imaginary solutions are there. We need to remember that anytime we are looking at imaginary solutions, they always come in pairs. So you would either have 0, 2, 4, 6, 8, 10, 12, whatever, imaginary solutions. You can never have an odd number of imaginary solutions. So when we look at number 1, it gives us a graph. It looks like 1, 2, 3. It looks something like this. Now, it says that it has a degree of 5. So that means there are how many solutions then? There are 5 solutions. Now, remember, our solution is just saying where we cross the x-axis. Looking at this graph, how many times does it cross the x-axis? Just once. So when we're listing solutions, we would say that there is 1 positive. Oh, sorry, that's not in the positive. That's in the negative. Yep. So there's 1 negative solution. And then that would mean, remember, imaginary solutions come in pairs. So we would have 4 imaginary solutions. You do not need to find them. Just say how many there are of what. If we look at now, number 10 is a little hard to see, so I will graph it up here.
I can't see it.
Yeah.
How do you know how many solutions there are? Like, is there negative?
Well, like with number 9, we could see it cross the x-axis somewhere in the negative. So we know that there's one real or one negative solution, and then we don't see it crossing the axis anywhere else. So that means the rest of them need to be imaginary, which makes sense that there's four imaginary because imaginary solutions come in pairs. So they have to be an even number. So that checks out to us. If we look at number 10, here's what the graph is trying to look like. Go like this, and then it goes up, and then it's a touch and go here.
Oh.
Now, if we are listing solutions, we have one negative, and then one for sure positive, now this is trying to call things back to our, so right now we need to get up to a degree 4. Right now we're at degree 2. What did we look at with when we had a touch and go in number 7 that we did together back in number 7 on the paper? We had x squared, and that hit our axis, and it kept going. So when we have a touch and go like that, just like imaginary solutions come in pairs, that would count as another degree of 2 because it hits the graph and it keeps going. So we could count that as 2 more positive, but really what we need to see is that we have 4 real solutions. So, I mean, I'm not too worried about, yeah, we would count that as 3 positive solutions because we have 1 here, and then this counts as 2 when we're looking at degrees. So we have a negative, a positive, and then this counts as a double.
Can I go with one? Yeah.
Not yet. Yes.
So with number 9, the first one that is degree 5.
Yep.
All we would have to put is 1 real and 4 imaginary.
Correct.
Yep.
All you need to put for number 10 is 4 real, 0 imaginary.
Yeah, we don't like
Now, if we look at number 15, they do not give you a graph for those, right? So what you need to do for number, I mean, it's the third one on the page, but 15, 16, 17, is you need to throw those into your y equals, and just, you don't need to find what the x values are, where it crosses, but you need to put it in your y equals to be able to look at the graph and figure out how many real and how many imaginary solutions there are. What? So you hit your variable, and then the exponent button is on the far left side. Usually you just hit square because that's quick.
It's like on a keyboard.
Number 9 crosses and sentences at 1 point.
Yeah, don't bully people.
Is that
How do you do, bro?
that's the one negative solution. And it doesn't cross
Me?
so 0.
Are you copying?
There's 4 imaginary.
So I stole the worksheet from Mrs. Stone, and she cuts problems out of like 5 different worksheets, and then glues them onto one piece of paper, and then runs copies of them. Yeah. She's not too good at downloading and using Microsoft Word, so she just prints them all off and just cuts them out. So our numbers are all over the place.
Then you go from like
8.
then you go 10 to 15.
Exactly.
17 to 14.
Yep. Exactly. Yes. Imaginary numbers come in pairs. Good. Good.
Imaginary what?
Imaginary numbers come in pairs. I think you have enough information to finish the rest of that page. Run through a couple of that.
You guys might need to Is this really the percentage? I have 0 hand. That's it.
It's broken. You have to go
Okay.
Windows. I don't know how to fix it.
Don't hold me. Sure did.
I wrote them all at once.
You did not.
Yes, it was 3 hours long. I was up to like
Oh, it does graph. That one's very weird. 17 graphs so weird. That's not how graphs go. There's only one positive solution,
Oh, wait.
right?
How many positives?
Yeah, there's 2 negatives.
I don't know.
That's
I'm
bad.
gonna say it's 2 positives. If I guess it, yes. Just 1.
2 zeros. What do you want?
Negative. Oh, right. Right. No, this is half. 3 positives. 3 positives, 1 negative.
oh.
Yeah. Yeah. There's 2 positives, 1 negative.
One positive.
So,
Next time, take it easy.
because the biggest 3 is 3. Oh, okay, but how do you know it's Unless so it has to always be even.
Why did I do that then? All right, one more thing we need to look at really quick. Uno más, uno más. So, we need to talk about one more crazy idea. Well, it's really not that crazy. You already saw it in Algebra 1C, but we're going to review it. Okay, I know. I was just kidding. So, let's see what happens. We're going to skip that one. Let's see what happens. Let's throw back to imaginary numbers. And let's see what happens when we FOIL this. 9i squared, sweet, minus 12i plus 12i minus 16. Now, what's going to happen to these middle terms? They're going to be gonzo. Hey, stay with me for a couple more minutes. You guys have been doing really good. Now, the thing that I want to point out is what's kind of interesting about these two terms that we started with. There's something kind of interesting. They're the same, but not really. Exactly. One of them, they're the same, except one is positive and one is negative. We would consider these two terms, where one is positive, they're the same, but not really. We would consider these to be called I gotta spell it right. Conjugate. There we go. A conjugate. Conjugate. Gate. And it kind of, let's look for a second. Conjugates come into play because when we have, like we said, imaginary terms come into pairs. Oh, do we have time for this?
No.
Dang it. No, we don't.
Yay.
Keep in mind you learned a new word called the conjugate, and we'll pick that up tomorrow.